Useful. Okay. So this is all the stuff we did last time. Vector spaces, subspaces, and writing things in terms of bases. Okay, this is quite a bit down. Here we go. So this is what we ended on last time, right? So we have the abstract picture of things, and then once we pick a basis, we can get things in coordinates. And the choice of a basis is what lets us go here, but there are many choices of basis. Right? So this is not, it's not canonical, is what they say. It's like the isomorphism of a vector space with Rn is not canonical. Okay. Okay. So let's go on to dual spaces. Okay. So first thing to note is that Hom VW, this thing that I defined last time, which is defined as this definition. So I'll put this here. Defined as the linear maps from V to W. This space itself is a vector space, and it has dimension V times dimension W, right? And it's a vector space just by, similar to how the functions on some set were a vector space. Sorry, the real valued functions from some set were a vector space. This is the same thing. So like if you have two linear maps F and G from V to W, then you can define F plus G as the function which takes in a vector V inside of big V and spits out F of V plus G of V. And then also you can imagine the scalar multiplication works the same way too. Okay, so it's kind of the same procedure as when you were mapping things to R, and I said that was a vector space, like the continuous functions on a topological space. Continuous real valued functions on a topological space form a vector space. So it has mostly to do with the vector space structure on W. That's what we're using here. Right. Okay. And in fact, if we pick bases for everything, right, dimension V, dimension W, are N and M, then this Hom VW space is, using a basis, we can show it's isomorphic to the space of N by N matrices. Right? And so this, if we think of these as the linear transformations from Rn to Rm, this is the isomorphism between the two spaces. Okay. Okay. So maybe it's just good to know that this is a vector space. That's like one of the important things. You can add functions, you can add linear maps between vector spaces together. Okay, so the first thing we're going to define is a linear functional, and it's not some new thing. It's just a linear map from V to the base field R. Okay, and if we were working with a different field underlying all these vector spaces, we would just go V to the base field F. Right? But of course, I have R for this whole notes document. And so, in other words, it's an element of Hom VR. Okay, so the elements of this is the space of linear functions. Okay, and so the dual space is going to be exactly this space, the space of linear functionals on your vector space. Okay, so if you have a vector space, you automatically have something called the dual space, which is the space of linear functions defined on that vector space. Does that make sense? Cool. Okay, so some examples of linear functionals I'm doing here. If we have our vector space as the space of n by n matrices, then you could define a linear functional as the trace is a linear functional. Okay, if we just sum the diagonals of the matrix, this is known as the trace. So here, if A is the matrix, right? I wrote out the trace sum is all the diagonal entries. This is linear. You can show that this is linear in, remember this is linear in all the entries of the matrix. These are the components of the vector space V here. So, and it spits out a real number, right? So that's basically all you have to check. Is it a linear function, and does it just spit out some scalar quantity? So this is a linear functional. And then here's an example for this infinite dimensional space that we had before, these continuous functions on R. If you define a functional by if you take an element f inside of your vector space, then define alpha of f to be the integral of f of x from 0 to 1, then of course we just get out some real number. And I mentioned before the integration is linear in the function. Integral of the sum of two functions is the sum of the integrals. Okay. And so this is a linear functional. Okay. I should say this isn't the only thing you check, right? You also have to check the other one. I'm just integral of lambda times f is lambda times integral of f. But yeah. Okay, so these are just some examples of linear functionals. But so the dual space is the space of all these linear functionals. Okay. Okay, so now we're going to work with the dual space and like, how does this is now a new object to look at in terms of like what happens when we put a basis and like what is a concrete version of it and stuff like that, right? So if we have a basis for the vector space B, we can define this dual basis to be as this basis, which is defined by the following rule, right? So I have a lot of indices going on here, but all the indices go from 1 to n. There's a little bit of a mess here, but dot, dot, dot. Okay. So the basis is these bi vectors, I going from 1 to n, and I want to define a bunch of linear functionals, so a bunch of elements of v star, and then later I'm going to claim that this forms a basis. Okay, but right now I'm just defining n such linear functionals. And alpha I is going to be defined as, well, to define a linear map, I only have to tell you what it does on the basis, right? Because that determines the entire linear map, right? So I'm just going to define how does alpha I act on this entire basis, bi, right? So alpha I acts on bj by giving out the Kronecker delta function, if you've heard of this. This is the Kronecker delta. And it's defined exactly in this way, which is if I and j are equal to each other, then it gives you a 1. And if I and j are different, then it gives you a 0. Okay, so they're kind of elements that are paired up with basis elements, right? So alpha I gives you a 1 if you put in bi, and it gives you a 0 if you put in anything that's not bi. Or if it gives you a 0 if you put in any basis element that's not bi. Okay. And then you just say this is a linear functional, so how does it act on any other vector in V? Well, it acts linearly, and it can just be reduced to how it acts on the basis. Right, do we remember the statement from yesterday that like a linear map is defined by what it does on the basis? Okay, so alpha I forms a basis on V star. So this is something that should be proven, but I'm not going to prove it here. But this set of n vectors forms a basis for the space of linear functionals. And so in particular, that implies that the dual space has the same dimension as V itself. And because anything, the only interesting fact about a vector, like a finite dimensional vector space, is its dimension, because then we can just say it's isomorphic to Rn, right? So all of these are isomorphic, maybe not canonically isomorphic, but once you pick a basis, V and V star are both isomorphic to the same Rn, where n is the dimension of both vector spaces. Okay, so that kind of makes sense as the dual. I guess the word dual has this connotation that if you do it twice, you get the same vector space back. And that is true, especially for finite dimensional vector spaces. I think you have to be careful if you're doing infinite dimensional vector spaces, but there's another fact that the double dual is equal to itself, or canonically isomorphic to the original vector space. Okay. All right, so now if we write everything out in terms of matrices, right, we have a dual basis. What does the dual space look like? Well, the dual space looks like this, the original vector space we identify with Rn after using a basis. And once we do that, the dual space looks like the maps from Rn to R, which is the same as just n by 1 matrices. Okay. And so these are going to be row vectors. Okay. And we want to think of them as linear maps on the column vectors, right? If we multiply this row vector by this column vector, we get basically the dot product between these two vectors, right? Which is written out like this. Okay. But here you do want to think of this. This is a different type of object than this, technically. All right. So if we look at, we can, right. So this is kind of confirmed, right? If we look at the dual basis to a regular basis, right? If we have E1 through En as our standard basis for Rn, then the dual basis, I claim, is this thing where we just have one. It's the corresponding, like you take these and transpose them sort of deal, right? Where you just have a 1 in the first spot and then zeros everywhere else. And you can check if you multiply the row vector that's just a 1 in the ith spot, and you multiply it with the standard jth basis vector, there's just a 1 in the jth spot, you will get 0 unless I is equal to j. Right? And this is the defining property for the dual basis, right? So I can define this basis for the dual space, and I confirm that it is actually the dual basis for the standard basis that I wrote down here. Right? And then if you were to change to a different looking basis for V, for Rn, the dual basis would change in some other weird way. Yeah, we didn't talk too much about like transforming bases and transforming vectors. But usually it's just like hitting it with some invertible matrix. Right? But if this were a different basis, this dual basis would be different as well in some kind of corresponding way. Great. Any questions about dual basis? Okay, so there's one really useful property about the dual basis, which this little thing is covering up. If you have a vector written in components in a certain basis, I, and then if alpha I is the dual basis to bi, then what happens when you apply alpha I, just the ith dual basis vector, to the vector v? Well, by linearity, it passes through all of these coefficients, v1 and vn, and hits just the basis vectors. But then when alpha I hits the basis vectors, all of them are 0 except for the ith one, right? So the only one we get left over is this ith term. And then this is just equal to 1, so we just get this coefficient left over, right? So if we look at this as a result, the ith dual basis vector applied to any vector spits out the ith component in the original basis, right? And so we can use this to kind of like refer to what is the ith component of V, right? So you could write down a statement that's like, well, V is equal to the sum of VI, oops, BI. So this is just a statement that is true when we learned about bases, right? If assuming that BI was the basis of V, right? But then what is VI? VI is equal to alpha I of V. So we could write this as alpha I of V BI. Okay. I mean, this may not look like much at the moment, but it's like it's kind of like a self-contained little statement about basis and dual basis. So I promise you'll see something that's close to this stuff in the geometry class. Like this is a very useful property to have to like use about the dual basis and stuff. Okay. All right. Does everyone make sense? Sorry, does this make sense to everyone? How this little blurb worked? Okay, so there's one other thing. I think this is maybe the last thing about dual spaces that I just want to define, which is, let's say now we have a linear map between vector spaces. Then we can define this map that goes between dual spaces, and it goes in the opposite direction. So we define the dual map to F, defined from W star to V star. And it's defined by, okay, so we have to set this up kind of carefully, but for every dual element in W star, we need to spit out a dual element in V star, right? So we start with an alpha in W star, and we want F star of alpha to be in V star. Okay, but now F star alpha is in V star, and I want to define what this is. Well, to define what a element of V star is, I need to tell you how it acts on all vectors in V, right? Because this is a linear functional on V, going from V to R. So to define this, I'm going to go through, okay, let's pick a vector, an arbitrary vector in V, and F star alpha acting on V acts in this way. Okay, so this is kind of this whole thing acting on V. Okay, and it's defined as alpha of F of V. Okay, so you can go in and check that all of these make sense. Little v is in this space, in the vector space V, then F of V is in W, and then alpha is a linear functional from W to R, right? So if we look at this little picture down here, here we have V, W, and then alpha is a map from V to R. I just drew it like this because it kind of makes sense that this is like a ground field sort of thing. And then F maps this way. And I'm saying start from some arrow from W to R, and I want to end up with an arrow from V to R using F. Okay, so it's really just, you can see from this picture that it's just you pre-compose F and alpha. Right, so you could imagine F star alpha. You could also define it as alpha composed with F. Right, and composing these arrows, we get an arrow from V down to R. And that's all we need for it. We need a linear map from V to R. But the actual map from, right, if we just look at it as points in the dual space, you took an alpha here and you mapped it over to F star of alpha in here. Okay. So this is called the dual map. It's also called the transpose, and it'll make sense why it's a transpose in a little bit. I'll write things out in bases, but you can expect that the matrix form for this thing will be the transpose. It's also sometimes called the adjoint. Some people, I guess, may not prefer to use the adjoint unless you have a dot product somewhere involved. And I didn't really talk about dot products that much here, but you can look more into why it makes sense to call it the adjoint. If you know what the adjoint is for something. Okay, any questions about this definition? So you'll see this a lot. This is also maybe another word is maybe like the pullback. Map or something. Because you're kind of pulling backwards instead of going forwards. Okay. Okay. If no questions, we can move on. So why is this dual map called the transpose? So let's write everything out in bases and see if it makes sense. Right. So let's start with a linear map. Well, I guess I'm not proving this theorem, but this is the theorem that I kind of just stated earlier. But the theorem is, if you have a linear map and you write all these vector spaces in terms of bases, right, then you have a matrix representation of the linear map F, right? We talked about this last time, where we use both the basis of V and the basis of W to express the matrix of F. And then we can look at the dual bases for V star and W star, dual to B and C. Okay, so put bases on everything. Okay, basically this whole picture up here, which I should rewrite down here. So, right, the V, there's W, and then there's a dual space W star, and there's a dual space V star. And we get a reverse arrow here. And this is also just a linear map between two different vector spaces. So if this has a basis and this has a basis, then we have a basis B here, and we have a basis C. And we have our dual bases, C star and B star. And in terms of these bases, F star has a matrix representation. And so the theorem is just the matrix representation of this is just the matrix representation of this, but transpose. Okay. And by transpose, I mean like transpose of actual matrices. Okay, but you have to use like the corresponding dual basis to be able to say that. All right, so sometimes F star itself is called the transpose without even writing down any bases. Okay, I think that's everything I had as material for linear algebra. So we're done with linear algebra. Stuff to look further into is this thing called the rank of a linear map. You can see what that's defined as. And then there's some stuff about multilinear maps and tensors. These kind of go together. I didn't go into defining these just yet, but you may define them actually in the manifolds class because they're pretty useful for formulating some stuff. Okay. And then also the determinant function is quite useful because you can define it abstractly. You don't need a basis to define it. Although if you have a matrix, there is this algorithm to compute the determinant. The determinant is also just defined as this antisymmetric multilinear map on n copies of your vector space. Okay. And so I think that property is also just very useful to this sort of abstract axiomatic definition of the determinant is very useful way of looking at the determinant. Okay, but I think that's everything. And then I mentioned the reference last time was just Hoffman and Kunze was my book that I used. I think I wrote it up above somewhere else, but I'll leave that here. Okay, any questions about just linear algebra stuff? Otherwise, we'll move on to multivariable calculus, and it shouldn't be that much longer. Cool. Okay, I'm just gonna